So it is a pleasure to have here today Ulf von Barth. He was for many years a professor in Lund. Thank you for coming. We will start maybe from the beginning.
Okay.
What made you choose physics as a topic?
Well, it turned out that I was extremely interested in mathematics as a young person, and already in school I had already finished quite a few of the university courses in mathematics. But then I was a little bit afraid about being a mathematician, because I realized to make any impact at all in mathematics, you have to be extremely clever. And I, of course, didn't know whether I was clever enough. So, but if you go into physics, on the other hand, you can make yourself useful, but not being so clever. so that was the idea. So that's why I went to Chalmers instead. I got an offer from the professor of mathematics at the University of Göteborg. To go into mathematics, but I decided to go to Chalmers and study physics instead. So that's what I did.
And at the beginning you did particle physics.
Yeah, because since I was interested in mathematics, and particle physics is more mathematical than other branches of physics, so I decided to go into particle physics. And did a lot of formulas. Spent a whole summer filling 400 pages with formulas and got a little bit fed up. And then I met Stig Lundquist, a fantastic, enthusiastic person who told me about frequency-dependent potentials in solids. And I was completely taken by his persuasive capacity. So I went into solid state.
Where you could also do mathematics.
Yes, but a little bit less.
A little bit less. Then you were teaching assistant, you taught, and then in the end you got an offer to do the PhD with Lars Hedin in Lund.
That's right.
That's where you met Lars Hedin?
No, I had him as a teacher at Chalmers on the solid state courses. So I met him before, but he actually got a chair in Linköping first. And since I then had talked to Lars Hedin, and he's given me a couple of problems to start to do research in solid state physics, I became a teaching assistant in Linköping, which was kind of a wasted year as far as research is concerned, because it was mainly traveling and teaching, because I still lived in Göteborg and taught in Linköping, which is across the country. But then Lars Hedin got the offer to become professor in Lund. And then he had a choice then whether to stay in Linköping or to move to Lund. It's hard to know what made him choose Lund before Linköping, but probably it had to do with his wife, who is from Skåne, which is a little town called Eslöv, which is next to Lund. So she probably played an important role in this decision to go to Lund. And when Lars Hedin moved to Lund, I had no choice but to follow him. So that's how I ended up in Lund. And this was 71.
Then you started your PhD studies with Lars.
Yes.
But the first topic was not exactly appropriate, right?
Well, it was a very good problem, actually. But there was a guy there, a physicist, a very renowned physicist called Leeuwen, who was a frequent visitor he was a friend of Lars and often came. I think he had a sabbatical in Copenhagen. He often came to Lund, mainly doing Hubbard theory and things like that. And he heard about my problem, which was to use GW to calculate the position of the F levels in the rare earth metals. I think it's a very nice problem now, of course, but it is a difficult problem for a beginner. And that's what Leeuwen told me, and I was a little bit discouraged, and Lars was angry with this guy for telling me off, so to speak. But then Lars gave me another problem, which was to generalize density functional theory to the spin polarized case, which I did then, and it didn't take me more than a couple of months.
Well, I have to say, even now, if I was given that task as a PhD student, I would be afraid. But and that was the birth of spin density functional theory, the theory that we now use essentially.
Yes. Yeah.
So what did you do the rest of your PhD if that only took 2 months?
Well, I first started to generalize density functional theory to the relativistic case, but Lars Hedin was not very fond of density functional theory. So he said that he wanted me to do something else, and he sent me off to the Swedish defense establishment in Stockholm, where they were experts on doing band structure calculations. So he wanted me to learn how to do band structure calculations. So I learned how to do APW and KKR and stuff like that. And then I did some papers together with the people up there in Stockholm on band theory, and then of course doing then a little bit using density functional potentials. So and the Kohn-Sham potential.
It may sound strange nowadays that there were people that were not really convinced by density functional theory at the beginning.
But I mean, in those days, there was the X-alpha mafia. Okay, that's a Slater group. I mean, Slater is a giant in physics, no doubt about that. But and he had all these followers like Keith Johnson and John Connolly and I don't remember all the names now, but they were doing X-alpha theory. And X-alpha, if you might know, it's like an average of the self-energy over the Fermi surface. And it gives you a particular value for this density functional potential, and then you have a fudge factor called alpha, which you could vary to get better results, and that was the predominant. So, but then I met at a conference in Exeter. I met two persons which made a big difference in my life, and one was Art Williams, who was doing density functional theory the correct way, meaning using the Kohn-Sham potential instead of X-alpha. So that impressed me about Art Williams. And then I also met Ole Anderson at this meeting in Exeter in '72. And Anderson had his LMTO method. And everybody else laughed at him and said that this is ridiculous and so on. And Ole Anderson was jumping up and down at the stage, calling everybody else idiots. He was very upset by the fact that they didn't understand the beauty of this method. But I did, so I invited Ole Anderson many times to Lund to teach us about LMTO.
And eventually, in your group, the first LMTO code
was
written.
I mean, Ole didn't want to program himself, so we decided that my first PhD student, Günther Grossmann, would do the programming. So he actually had the first LMTO code in the world that we made very good use of later on for the X-ray problem.
And you were telling me before that you could run very large systems.
Yeah, well, I mean, we did 16 atoms per unit cell. To do the X-ray problem, we wanted to see how the core hole in one atom would affect the charge density around the excited atom, because that would influence the spectrum, the following X-ray emission spectrum. So we did 16 atoms per unit cell with one atom with a core hole and all the other ones neutral normal atoms. And then we saw how the charge density was building up. But I mean, in those days, nobody could do 16 atoms per unit cell, but with LMTO, it was possible.
Maybe let's go back a little bit to Lars Hedin.
Right.
How was working with him? How was him in the day-to-day scientific life?
Lars Hedin is a little bit, or was a little bit of a shy person. And he was, I would almost say, the perfect thesis advisor for myself, because I like to do whatever I like to do, so to speak, with as little influence as possible of a thesis advisor. And in that regard, he was perfect. Mm-hmm. But also, he created a fantastic atmosphere, because he had all these people that he knew. I mean, there were Nobel laureates passing through Lund on a daily basis, and Lars Hedin would always invite his PhD students with these Nobel laureates to visit time with in his home with his wife and children and so on. So we were kind of buddies with the people like Bob Schrieffer and Walter Kohn, Sir Neville Mott and Maurice Rice. And I mean, this was... It was a fantastic atmosphere for a young person to meet all these famous guys.
Mm-hmm. So, besides density functional theory, GW and Green's functions were very important in the world of Lars Hedin.
Yes.
In your world.
Yes.
So then you also worked in this subjects, right?
Yes. As a matter of fact, one of the first things we did then was. We did an approximation that was designed by Walter Kohn, not in the Kohn-Sham paper, but in the Sham-Kohn paper, which followed that, which is a kind of a local approximation for the self-energy. And we applied that. And I remember presenting the results in a conference in Taormina in Sicily in '73. And Walter Kohn was there. And that was probably the first encounter with Walter Kohn. And I remember after the end of the conference, Walter Kohn spent all his recapitulation of what had happened over the conference on my talk, which I was extremely flattered at the time, of course. So that was my first positive encounter with Walter Kohn.
But you met him several times afterwards.
Yes, and my later encounters were not so pleasant.
Would you like us to tell us something about it?
Well, I had designed a theory which I called the spherical solid model, which means that you take an atom in a solid and you take the crystal potential, you just take a spherical average and you treat the thing as a single atom in a spherical potential. Now the important thing is that you could put a proton into the electron gas, and you could change the density of the electron gas. And you could see when a bound state drops out. Now, in our first calculations, we found a discontinuity in the total energy of this system when a bound state dropped out. And we then remembered a famous theorem by Walter Kohn called the Kohn-Majumdar theorem that said that everything has to be continuous.
Oh.
So this was a kind of a counterexample. And we wrote to Walter Kohn about this. We sent a preprint to Walter. And we got a very short message back from Walter Kohn. And it just said, please tell me to what journal you intend to send this piece of work so that I can make sure that it will never appear.
Did you manage to publish it in the end?
No, but we realized that it was, we went back, we had made a mistake.
Oh.
Well, the mistake was kind of obvious in retrospect, which it often is, right? The mistake is that we were kind of, we had Leo Farley, so we kind of read the Hubbard papers and we're very aware of the U, the famous U, okay? When you put something on an atom, then it's an additional U to put one more electron on that atom. So when a bound state dropped out, we just occupied that with one electron, that occupied state. But of course, this is wrong. Immediately, there is no U when a bound state just drops out, because the wave functions are so spread out that U is 0. So you should put 2 electrons on that side. And if you did that, the curve was perfectly smooth, just as Walter had predicted.
So Walter Kohn was happy after all.
No, but then came the next encounter with Walter Kohn, because we then went through the proof of Walter Kohn, and we thought we had discovered an error in Walter Kohn's proof of the Kohn-Majumdar theorem. So when we met Kohn in Paris about a year after, I told him that we think there is an error in his proof, and he was very upset. And I remember going to a party with Walter in Paris. He used to go to a person called Chuck Summers, a funny American physicist who had abandoned his country. He said that France is a civilized country and the US is a primitive country. So but he had parties, and Walter Kohn would always go to those parties. Walter Kohn lived with Chuck Summers when he was in Paris, which he was often in Paris in those days. And we had a party at Chuck Summers' place, and everybody was, of course, gathering around Walter Kohn, the famous man. Everybody wanted a piece of the action around Walter Kohn, and I was standing there too. And then we discussed the temperature of the water in California, in Santa Barbara. And I said, isn't there a cold? Isn't it pretty cold in the water outside Santa Barbara? And then Walter Kohn turned around to and looked at me and said, "Aren't you ever right about anything?" And I was completely devastated. So that was my second encounter with Walter Kohn.
I suppose that over the years you have more pleasant encounters.
Yes, of course we did. We wrote a review article. I mean, that was Stig Lundquist who invited several people to write a review article on density functional theory. And Art Williams and myself was to write the large part on applications and things like that. And then Walter was also writing a part, but he was wise enough to invite Priya Vashista to be his co-author on his part. But they finished their part pretty quickly, whereas Art and I dragged out for years to submit our part. And Walter was getting more and more annoyed because he was writing us letters saying that by the time his article would be published, it would be obsolete because because we were taking such a long time. But then, of course, at this conference that we talked about before in Al-Kabidech in '83, I could tell Walter that our piece was now finally published. And he was very pleased. Yeah, so. But then, of course, I had more encounters with Walter after that. More all of a pleasant sort.
Let's maybe talk a little bit about this conference in Alcabides in Portugal. There were a lot of people there, a lot of people who were very important in development of DFT.
Yes.
That's where you told me you met Hardy Gross.
That's right. He came to pick us up at the airport and drove us to the conference site. But I remember a funny incident there in the morning of the conference. The people who talked in the morning were kind of devastated because when they looked out over the audience, they could see most of the people half asleep in the audience. And of course they thought, maybe, am I this boring, or is the topic that I'm talking about so uninteresting? But then I went to talk to the personnel organizing the conference and said, I don't think you're giving us coffee in the morning. I think you're giving us chicory, which is kind of common in both Portugal and Spain. I mean, in Spain, if you buy coffee, you should avoid the thing that says mezcla on it. You should buy the stuff that says Arabica. That's the real coffee. And when they switched to real coffee, or upon my suggestion, everybody was happy in the morning and the conference went smooth again. That's kind of a funny story.
So in that conference, you presented your work on the eigenvalues of the Kohn-Sham equations.
Yes, that's right. And as I said before, I started the business by doing reverse engineering to find, for the Hartree-Fock case, I did Hartree-Fock calculations of finite systems, and then I did the same calculation with potential, with variational parameters, and I varied the parameters until I, in a simple one-body calculation, reproduced the exact density of Hartree-Fock.
So we inverted the Kohn-Sham equations
Right.
to get the Hartree-Fock potential.
It's now referred to as reverse engineering,
Exactly.
if you like. Yeah. And but of course, as the eigenvalues are very hard to pinpoint on an absolute level. Because you could put the atom in a box, and if the box is pretty wide, you can make it very deep, and it's going to shift all the eigenvalues by a large amount without affecting the density by almost nothing. And so you need the eigenvalue theorem, which says that the density of any finite system is governed by the ionization potential, which I proved. I constructed a proof of that. But in discussions with Mel Levy, who had several papers on that, he has actually, in those days, I considered Mel Levy to have the nicest formulation of density functional theory. He was the one that had the constrained search approach to density functional theory, which he published in some obscure American journal of physics as a little note or so, but it's a beautiful paper, okay? So I had very high regard for Mel Levy, and he said that he had actually proven what I had proven earlier than I did. And I asked him, why didn't he publish this? And he said, well, the referee didn't like it, so it was thrown out.
Well, that happens to the best of us. And in those days, so we are end of the 70s, beginning of the 80s, there was already a community that did density functional theory, that did GW, that started with Lars Hedin. Was there the conscience, people believe and understanding that it would become such an important field as it is now?
No, I think the attitudes has changed. Of course, first when I started out in physics in the early 70s, then people were very skeptical because you had the whole Slater group doing what they refer to as the X-alpha method. And then Walter Kohn came along and constructed the Kohn-Sham potential, which where the potential is, well, the local density approximation of that potential is coming from the electron gas and so on. But people were still skeptical, but it was gaining ground. And then after 10 years, I would say, in the beginning of, or late 70s, people switched around completely and got the completely opposite attitude, that if you do the right thing, if you have the exact potential, then every number is going to come out bang on the experimental results.
And you also have a nice story about that with Marvin Cohen.
Yeah, I didn't believe that, because I've done, of course, this reverse engineering thing, so I know exactly where the eigenvalues were, and I also know what the total energies were, and I also knew that the local density approximation always gives overbinding for all finite systems, and the local density approximation to the that's the exact density functional theory, gives overbinding, but also the local density approximation to the exact theory kind of exaggerates that error in exact density functional theory. So in order to prove that point, I met Roberto Carr at IBM, who was a postdoc of Socrates Pantelides at the time, doing impurity calculations in semiconductors. And he was very excited about the idea, so we did this work together where we really mapped out the local density approximation for the cohesive energy of silicon. We took the most common material that there is, okay? Yeah. So we took silicon and calculated the cohesive energy and ended up with some 5.3 electron volts. And of course, we looked up in a recent paper published by the Berkeley group under Marvin Cohen, which, of course, with the attitudes people had at the time, ended up bang on the experimental value, which is like 4.63 electron volts, something like that. And I went to a conference in I think it was Santa Barbara, it was in California somewhere at least. And I was at IBM at the time, so I was sent out by IBM. And I presented my results there, and of course there was a big commotion in the audience, and when my talk ended, 400 hands flew up in the air. I think it was Michael Schlitter that said, are you aware of that your results are contrary to the results recently published by Yin and Cohen on the same thing, on the cohesive energy of silicon? And I said, yes, I'm very much aware of that, yes. And Michael said, what's your explanation for that? And I said, why don't you direct this question to Marvin Cohen, who's sitting here in the front row? But he was not too pleased about that.
Ulf, over the years, you have collaborated with Carl-Olof Almbladh. It's a lifelong collaboration.
Yes.
So when did this all started?
Well, we met at Chalmers. I guess we both had gone to Lars Hedin's solid state courses. And then when Lars became a professor in Linköping, we had already decided to choose Lars Hedin as our thesis advisor. Of course, we were both students of Lars Hedin, and it was natural that we talked a lot, right? And I went to Linköping to teach, and Carl-Olof went to Linköping to teach. So we were teaching like every other week each, so to speak. And then Lars Hedin became professor in Lund. We were given the choice to come with him to Lund, and both Carl-Olof and I decided to go to Lund. So we started to do our PhD work in Lund. But we got kind of different topics. Lars Hedin has actually started already at Chalmers, but not having Lars Hedin as a thesis advisor, but Bengt Lundqvist as a thesis advisor. So he was doing photo emission for a while. But then when he met Lars Hedin, it turned out that the way he had started to approach the photo emission problem using response theory is ill-defined. So he switched and was given a different topic by Lars Hedin, was incomplete relaxation, which means that if you create a core hole in a solid by an X-ray, say, and then this core hole will eventually be filled. But if the excitation that you create in the initial process of creating the core hole have not died away from the area, you can pick up energy from that initial process in the subsequent emission process. And this is called incomplete relaxation and gives structure in the spectra.
And this was his topic.
And this was his topic. It's a very complicated topic. You need 3 current correlation functions. So Carl-Olof actually got stuck for a while. He finished the problem, and it was a very nice problem, and actually one of the highlights of his career. But he got stuck for a moment, and then I was doing much simpler problems. I had this spherical solid model that we talked about before, where you put an atom into the electron gas or in a spherical solid. And I asked Carl-Olof to come and join me to work on my problems instead, and he said yes, so we started to collaborate. And we did several papers together at that time, before he went off to the US for a sabbatical at Urbana. And but then we actually continued to collaborate also when he was in Urbana. We did a problem on X-ray structure and when he was in Urbana. And we have collaborated ever since. And actually one of the highlights of our careers is one day, and this was late in, it was around 95 or something, 96, something like that. Carl-Olof came into my office, and he said he scrutinized the review paper by Hedin and Lundquist, the famous review article on many-body theory, GW and so on, in solid-state physics. He scrutinized that and said that Lars Hedin had actually suggested that you could use the screened interaction, which Lars Hedin called W, as a variable in a variational formulation of many-body theory. And I got extremely excited by this idea and started at my desk and worked out the theory to third order in perturbation theory. And it worked, okay, it was fantastic. So I got even more excited and rushed into the offices of Robert van Leeuwen, who was then one of our postdocs. And he got excited too, of course. And he's a brilliant student. And he, shortly after, came with a proof of the theory that we call the psi-functional to infinite order perturbation theory. So this was the start of many, many papers on this. Carl-Olof, myself, Robert, our students, all worked on this for a while. And I don't think the last word is said here at all. I mean, there's so many things that can be done here, which other people have taken up the same thing, like there's people doing dynamic and mean field theory and Kotliar and people like that. So I think there's many more things to be done in this area.
As we are just mentioned, Robert van Leeuwen, there was another very interesting development those times in that time related to time-dependent density functional theory.
Yeah. Now that was. It was a conscious decision that we would go into density functional theory. So we I talked Robert into doing this. Of course, he had already started to think about it, so it was kind of natural discussion between ourselves. And he kind of rectified or improved on the famous Runge-Gross paper from 86 or something like that. There was this contradiction in the Runge-Gross paper. I mean, if you taking functional derivatives, it's symmetric in the arguments, okay?
And not causal, the response
And
functions.
then it's not causal, Robert managed to resolve this issue. And you told me today that, and I should have remembered myself, that Vignale did the same thing earlier, but Robert did it with the Keldysh formalism, which I kind of think he actually picked up from mainly from Carl-Olof in Lund in those days. And he did a series of papers on this topic with time dependence. But what actually happened, Robert got his papers out, and then he got another paper out with the experimental group in Lund. We had a very good, tremendous physicist called Andrew on attosecond lasers, an experimentalist, and high harmonic generation, and we tried to involve her in this. So Robert did a work with one of her students. He was called Dimitris Lappas, I think, but on the double ionization of helium using lasers. So that was a concrete thing that came out of this. And of course, Robert has continued later on with this.
Yes, exactly.
He has also continued with the variational formulation. So he takes that one step further by introducing also not only first the Green's function, then the screen interaction, and then also the vertex function as a variable in a variational formulation of many-body theory. I have not seen so many applications of that yet, but it's pretty complicated.
There is still time.
There is still time, yes.
Ulf, you spent most of your career in Lund, but you had a series of extended stays in the United States.
Yes, that's correct, yes. So as I said, in my early years, of course, most of the people that I know in those days were on the other side of the Atlantic. The German science, of course, first of all, it was kind of dominated by the Hubbard mafia. And also, it was not that, I would say it was not that prominent in those days. Of course, it was completely destroyed during the war. I mean,
We took time.
Germany was a fantastic country for science in the old days. I mean, think about their chemistry achievements in the early 19th century, or 20th century, but then it was slowly picking up, of course. But in those early days, when I started in the early 70s, the main place was the United States. So we often went to the United States. And then, of course, came the European Union, and they started research efforts, and they started this idea of networking. And I got involved in that when I was invited by Lucia, together with Lars Hedin and Carl-Olof, to Orsay or Saclay up at the hill. They had already started this idea. And it was actually Rodolfo del Sole was the originator of this idea. And then we got funded after a while, and we actually collaborated and had money, and we had yearly discussions. So the whole pattern changed from being the fact that we went to the US almost every year, several times a year, to collaborate with American physicists. And of course, in myself, then I often went to IBM. But after '92, you could say, or '93, whenever we got funded, the whole thing shifted, and we started to travel to Europe more and more, and less. In the beginning, actually, the European Union discouraged us from having collaboration with the US. And eventually that was breaking down, and we took in American physicists in our network, like Stephen Leeuwen, for instance, or Eric Shirley, or people like that. Many people, John Dreher from Washington State and Seattle. And so, but there was a change in research policy. There was also a change in funding policy, which is, I find kind of interesting, because when I was a young person in Sweden, the Swedish Research Council conducted evaluations of Swedish physicists. And they could choose 1 year, for instance, solid-state theory, the next year solid-state physics in general, including also the experimentalists, and they could choose semiconductor physics or different topics. And then they would invite, and that was the important thing, an international committee of evaluators. Because Sweden is a small country, and the tendency towards nepotism is very high. So in order to avoid that or minimize that, they would invite foreign. So it would be an English guy, an American guy, a French guy, and headed then by a Swedish guy who could tell them about how things work in Sweden and so on, where people are, their affiliations and so on. And then they made a ranking list. They went around, talked to the people, read their papers, and made a ranking list. And some people ended up on top, and some people ended up at the bottom. And those ended up at the top, when they applied for money, they just had to write a short note, I want money. And if they ended up at the bottom, they wouldn't get any money, no matter how well they wrote their application. And the people in the middle, they would have to struggle and write a really good application to get some funding. Now, after that, they stopped doing, I think that one of the last evaluations were done in '84 or '86 or something like that. I don't remember exact date now, but after that, the whole philosophy changed, and the philosophy was now to hand out money, a larger piece of money, to what they call creative, strong research environments. And that usually meant some guy who was a big operator and gathered a large group around himself. And the money was given to him, and as an individual scientist, you would have to go to this guy, cap in hand, bowing and ask for money, and the guy would say, what can you do for me? And then you get funded this way, of course. I think that is not a good way of doing science, doing funding.
It's a very complicated problem, the problem of funding of science.
Yes, because it's a thing with positive feedback. Because you give money to the guys who already have money, so to speak. Because those who have money can easily get more money. And those that do, it's like it says in the Bible, right? To those that have shall be given. From those that do not have shall be taken their last shred. Says in the Bible. Okay, but this, as a physicist, you realize that this is a system with positive feedback, and as such is unstable, intrinsically stable. Any physicist should realize that, of course.
And leads to Pareto distributions, which are very unfair in some sense.
Well, it's not very creative, because it locks things to structures. So, but that's about research policy. But it meant, of course, that the European science improved quite a bit by this networking thing, because the fact that we could collaborate and rather easily get money for collaborations and so on, I think that boosted European research quite a bit. One thing that I am not so fond of is the fact that the politicians in the European Union, they like to see results. Of course, they want to have a competitive industry, and so they now tend to require that in order to be funded, you should have some collaboration with industry, even in many cases where this is completely out of, because sometimes the difference between fundamental research and applications is so large that it doesn't make any sense for fundamental researchers to collaborate with industry. You just have to make some phony things in your applications. That's really not realistic, but just to...
No, it's a real problem for fundamental science
sometimes.
I know that you had some issues with physical review letters.
Oh yeah, should you...
Could you tell us the story?
Should I take the long version or the short version?
Maybe an average version.
Well, it all started... that's one of the highlights of my career. And that's this thing that we started with my student, Günther Grossmann, in Paris, doing these things that I talked about before with the supercell calculations of the X-ray problem. Then we discovered something that we named the final state rule, which means that if you want to describe spectra, you should do a calculation of the final state of a many-body process. So if you think about X-ray emission, for instance, where you have a core hole being filled by an electron from the valence band dropping down into the core hole, sending out an X-ray, the shape, the energy distribution of those X-rays that come out, should they be calculated in the initial state with the core hole or in the final state? Of course, all the such calculation, that's not really the correct thing to do, but which of these calculations is more close to reality? And it turns out it's always the final state. You do a simple one-body calculation of the final state, and you can add actually a singularity at the edge if you like. But that's what you're going to see in experiment. So, for instance, if you have a doubly ionized core state, so you have kicked out 2 core electrons. Now then, the initial state has 2 core holes, and one is filled by 1 electron. Now, this is a satellite spectrum. It's at a higher energy, and what is the shape of that satellite spectrum? It turns out that it looks very much like a one-body calculation will give you with 1 core hole present. Okay, many you can do it in absorption, and the same thing you can do atoms, let's say outside surfaces. You put a core hole, you can have very drastic changes. You have a core hole, it could pull down a resonance below the Fermi level. So the final state could be, or the other way around, absorption. You kick up and a resonance is being pulled down. The question is, what do you see? Because the difference is large, right? And it's again, in all cases we've tried, it's always the final state. Now, we wanted to corroborate that, or you could say almost experimental finding, by theory. And what we did was to solve the M&D model. M&D model means non-interacting electrons suddenly exposed to a attractive or repulsive potential. Okay, so there's not really any interaction involved. You just have this switching on of a potential. And that can be solved in different ways, but my student, I solved it by means of determinants, wave functions, and so on. And my student then solved it by means of transient Green's functions. And the champions there is, of course, the Russian group under Grebennikov and people like that. And so he did solve this problem with transient Green's functions. But it's a very numerically complicated problem because these Green's functions in time space decay very slowly. So you have to go very far out in time and so on. And what happens close to the edge is very far out in time. So that's what he did, and that was his thesis, and he worked a lot on that, okay? Then we had a friend of mine, Jerry Mahan, coming to Lund, and being the very smart physicist that he is, he immediately realized the importance of this work we had been doing. So, and then he went up to Chalmers, because Chalmers was the institution that had paid for his sabbatical, or half-year sabbatical. And then in the spring, a paper ended up on my desk from Jerry Mahan. And it was a sloppy calculation of exactly the kind that my student had spent months and actually more than a year on. And Jerry just wrote me, I guess you want to be in on this. And of course I wrote him back, what do you mean? I don't want you to be in on this. So I refused to collaborate with him under those circumstances. And he sent his paper off to the FISREV. And I said, we got to be quick now with some publication on this here. So we sent it off to the PRL. And we thought, I mean, it's supposed to be quick, but you know that PRL is never quick.
It's never
right?
quick,
That's
no.
not the reason why you send stuff to the PRL. It's for prestigious reasons, right? So anyway, it turned out that another person called Jack Dow, maybe in semiconductor physics, his claim to fame is that he'd actually been, I don't know, a running back or something at the Notre Dame football. He was very proud of that, and he was a big guy. He had actually done the same calculation as I had done with doing this Noether-Denominator problem with the determinantal approach. But he had a very sloppy way of calculating the matrix elements for the following transition to calculate the spectrum. And he came to the exactly opposite conclusion, namely that there is an initial state rule. Okay? So we sent off our stuff to the but he also sent his stuff to the PRL. And the PRL sent his paper to me to be refereed, and sent
Your paper to him.
my paper, or Günther's paper, to him to be reviewed. And he said in his review that if our paper were to be published, it would set back physics 10 years. So it was pretty flattering, actually, to have such an impact. But I was, of course, appalled. So, but I wrote to the PRL then and said that the only thing you could do is now, since before this is resolved, is that you either publish both papers back to back, let people decide, or you refuse both papers until the problem is resolved, right? They did neither of these things. They published Jack Dow's paper. And I, of course, was extremely upset by this, and wrote to the adjudicators, of, which was then my old friend Leo Falicom. And I asked, but Leo, how can you do a thing like this? This is terrible. And he said, well, you know, this Jack Dow, he stirs up such a tremendous noise if you go against him, so we didn't dare to do that. But what about me? So then I set up a piece of paper where I described everything that had happened without any judgment or judgmental phrases or anything like that. Just the facts which had happened. This and this has been written, this and this had been said, this and this happened, and so on. And of course, this resulted in a storm of people writing to the PRL. And the chief editor of the PRL wrote to me and said that this is terrible. You have actually tarnished the reputation of this prestigious journal. And then it was Wells, I think, at the time, who was the chief editor. I wrote him back and said that I'm glad to hear that, because that was exactly my intention. And then he said, he wrote me back and said, I'm sorry to hear this, and then he said that maybe you could continue to do refereeing for us, and I said, yes, that's okay, but I'm not going to publish any paper in the PRL anymore, and I never did.
Mm-hmm. Yeah.
I actually had an incident several years later when I had a student working on self-consistent GW, and this he had some very nice results and actually proof of the theorem. And the proof was due to myself and not to him. But he went around talking about it. And they urged him to send the paper off to PRL. Mm-hmm. And I said then that, you know, I promised never to send anything to the PRL, because I don't think the physics community is mature enough to handle a paper like the PRL. So I'm not going to do that. But on the other hand, I realized the importance of a PRL to your own career. Mm-hmm. So I'm not going to stand against you, but if you send it off to the PRL, which you're free to do, but you're going to take my name off it. And that's what he did, okay.
Mm-hmm. And the paper was published?
The paper was published in the PRL.
There were several personalities that marked you and your career during the years. We already talked about one, Walter Kohn, but yes, there were others.
Yes, well, of course, I should start by saying my thesis advisor, Lars Hedin, because he was the reason why I went into both density functional theory and GW and many-body theory. So, that, of course, that has been extremely important in my career. But on the other hand, we never collaborated. We had a couple of papers when I was a student together, but after that, we never collaborated that much, because I was given an advice by Stig Lundquist, who was the one who actually persuaded me to go into solid-state physics in the first place. He said that you could publish a couple of papers with your thesis advisor in the beginning, but then you should avoid doing that, because you have to establish yourself as an independent researcher. And if you publish with your thesis advisor, people are going to think that you can work without your thesis advisor, so to speak. And I know that Lars Hedin was extremely upset when I told him about this, and he got very angry. But of course, he's a very shy person, so he never dared to approach Stig Lundquist and make a row about it. But anyway, that was it was. So I never published that much with Lars Hedin, but it's needless to say, just the fact that I ended up where I did in physics is due to him, right? But then when you come to other personalities which have meant quite a bit to me in my research, is I've of course mentioned Walter Kohn, who I had several encounters with through the years, both of a very positive nature and a very negative nature, as we talked about before, right? So, and of course I have an extremely high regard for this person. I mean, he has contributions all over in physics, and there's almost not a single topic where he has not contributed. Think about just the old stuff like KKR. Yeah. What's K in KKR standing? It's Kohn, of course. Of course. So this has an enormous impact on me, this guy. But and the other guy or person that meant a lot to me was David Langers, and he was a friend of Bengt Lundqvist and a frequent visitor to Chalmers and also to Lund. Whenever he went to Chalmers, he usually went to Lund as well. And he, of course, had this very important papers on the X-ray problem, which I was preoccupied with in the early days with this work with Günther Grossman and so on. With the dielectric function up in the exponent and so on for the X-ray problem. So that was a parallel. But he was also one of those persons which is, so to speak, the really deep thinker when it comes to gradient corrections within density functional theory. And of course, John Perdue went to work with David. I think he was a postdoc with David for a while, and he got a lot of his ideas from David. So he's a giant in my world, so to speak. In addition to being an extremely nice person, he's a very humble, soft-spoken, very sharp guy who never tries to brag or... So it's an idol. And then let's say, what else did I mention? I mentioned Hardy. He's kind of the same personality. I mean, he's soft-spoken, very correct.
Very sharp.
Very sharp, yes. Very sharp, yes. So I have a big admiration for Hardy. In the early, I told you when I first met him in '83 at Al-Kabidech, yes, and then of course I didn't know. Then he had spent a lot of time with Hardy, I think, when just before that. But then came the famous Runge-Gross paper, and when we decided to really get into time-dependent density functional theory, we started this effort when Robert was there. When you came there a little bit later, but Thomas Kreib, he brought his whole group and gave a series of lectures in Lund on time-dependent density functional theory, including also the experimentalists. So that meant a lot to us in Lund, of course. And then there was a connection with Robert. I had Robert as a postdoc, Robert van Leeuwen, and he also had strong connections with Robert, right? So
there was a lot of exchanges.
Yes, there was a lot of exchanges. So, and then of course he also participated later on in our network. And he was, you could also discuss nuclear physics with, actually I did a piece on nuclear correlation energies at the end of my career, yes. But I discussed that with Hardy, and he was very full of insight into this problem as well. So
I was not aware of that.
No, but anything you bring up in physics, you can ask. And finally, I'll probably mention Jerry Mahan, of course. We spent many days together, and his wife driving around to different places in Sweden, in southern Sweden. His wife was interested in the glass work of Småland in Sweden, and so we're very good friends, in spite of unfortunately he passed away now a couple of years ago.
So you were involved in the very beginning of GW and of GW calculations for real solids.
Yes.
And there are some funny stories that you were beaten by the group of Steve Louis. And can you tell us more about that?
Yes, I mean, of course, being a student of Lars Hedin, GW was, that's the reason why he sent me off to learn about band structure calculation, because that's the starting point if you want to do GW calculation. So we did this sham-Kohn approximation. That was the first thing that I did. But later on, I had a proposal, and that was for when we had one of these evaluations that I talked about before in connection with research policy. And we had an evaluation, and my proposal was to do GW calculations to calculate the band gaps of the semiconductors, which kind of an obvious thing to do, right? And Lars Hedin strongly advocated this as well. And the proposal went in, and it got very favorably evaluated, and I got money for a postdoc, and that money was later used then for Ariasettia. But by the time Faraday Ariasettia came to me in '87 in August, and then Stephen Louis and Hybertson had already published the work on silicon, okay? So they beat me to it, so to speak. But then we decided to go for the transition metals and the transition metal oxides to see what's going to happen if you do GW for these systems, of course. And we found that for the quasi-particle properties, it was a real improvement. I mean, the band widths and so on became much better when you did GW as compared to local density approximation and so on. But there are, of course, many things that did not work as well. For instance, there is a spin splitting between the bands, and of course it's a magnetic material, so it was nickel, and that didn't improve. It was much too large in density functional theory, so and it didn't improve doing GW. So there is clearly something missing in that. And of course there is also the famous 6 eV satellite below the band, which is a satellite structure to the main band. And of course that's completely outside density functional theory, so that didn't appear either, of course. But the funny story here is, of course, that P.W. Anderson, and I usually emphasize this when I was giving talks on why did you do this problem? And I usually said that because P.W. Anderson said you shouldn't. Because his opinion was that a system like the simple transition metals, and especially their oxides, which are even worse, is way beyond perturbation theory from the electron gas, so to speak. It's a phase transition between transition metal and the electron gas, and a phase transition cannot be achieved by perturbation theory. So, but on the other hand, you have this feeling that if you do the bands in nickel with GW, you get very nice bands, right? So you cannot be completely wrong, right? Yeah. Of course, you cannot get the 6 eV satellite, but there must be something to it that can be treated by perturbation theory. And maybe, of course, the next thought is if you include some vertex corrections in GW, you might actually get very nice results, including the 6 eV satellite, maybe. I don't know, but we haven't tried yet. But it was kind of fun to do that then. And then, of course, after we achieved these results for nickel, I ran out of money for Ferdi, and he went down to Ole Gunnarsson in Stuttgart. And there he did the nickel oxide case. And of course, being in the group of Ole Anderson, he had to, because when Ferdi came, I had designed a new band structure method that would be faster to generate all the orbitals that was needed for the GW calculation. But now going to Stuttgart, of course, it was essential to use the LMTO, of course. So he switched to doing the LMTO. He did the nickel oxide with LMTO. But as I remember now, it was very sensitive how you started the calculation, where you put the bands when you started. So the result came out dependent on how you started the calculation. And then if it is, of course, inconclusive, so we could not really say what the right thing is. Yeah, I don't know if somebody else has produced results since then which are more conclusive on this topic.
Thank you, Ulf, for being here. It was a pleasure.
Yes. And I should thank you for giving me an opportunity to look back at my life. It's kind of I haven't looked upon it this way before. I've always been in the middle of it. Now I got a chance to look back at it.
It was a pleasure.
Yeah, it was a pleasure for me too.